All right, so this is the video on the proof of the second derivative test. Let's get right to it. Okay, basically what we need to show is that for it to be a local minimum, the second directional derivative has to be positive all the way around in any direction, 360 degrees. And for it to be a maximum, it has to be negative all the way across. If the second derivative, as it goes around in a circle, is ever positive or negative, then it would have to be a saddle point. So that's what we're going to check. For ease of notation, I'm just going to write the unit vector in the direction hk. So h is the x component and k is the y component. The directional derivative is given by the dot product between the gradient and this unit vector. So we're going to use the dot product computation, and we're going to do that twice because we're looking at second derivative in this direction hk. Okay, so the algebra does get a little bit messy, but basically you want to take the directional derivative of each half, and then if you expand it out, this is what we get. If you multiply out the h and the k and collect like terms, you're going to get three main terms. So the f double x h squared and two mixed terms that you can combine, and f double y k squared. So what we're going to do next is that we're going to factor out the second derivative with respect to x. So you're going to pull this out of each of the three terms. It only exists in the first term, but you could still pull it out by making up for it by dividing each term there. The next thing we're going to do is we're going to complete the square. So we have these two terms. And note that there's a h squared here and h here. We're going to add and subtract a particular term. In particular, it's the coefficient of h divided by 2 and then squared, right? That's what you're going to add and subtract. And we're going to get a perfect square here. And this is the term we subtracted to make that perfect square. I know I'm kind of going fast. This is a lot of algebra, but you could double check each of my steps. I don't want to make this video unnecessarily long. Let's see. Okay, so what we're going to do next is we've factored out fxx from all the terms. We're going to multiply it back in. So we're going to multiply it in front of the perfect square term, and the other two terms is going to cancel out one factor of fxx. And if you factor out k squared over fxx for these two terms, what we actually end up with is that the d term that appears in the second derivative test. This is the key factor. So how is this going to tell us if it's always going to be positive, always going to be negative, or is it going to switch signs? We'll note that when you square something, you're always going to get a positive number. So if fxx is positive and d is also positive, all of these terms that we're adding and multiplying is positive, so it's going to be a local minimum. If this is positive, but fxx is negative, then both of these coefficients in front is going to be negative. Negative times a positive number is negative, so this is going to be negative all the way across for any h and k. Okay, if this term right here happens to be negative, then this will have to switch sign at some point, because If you choose k to be, so h and k is gonna change as you go around in a circle. When k is 0, basically what we're gonna have is the first term is gonna dominate. So you have some positive number times fxx. And some other point, k is going to be, this term is going to be dominant. So you have a negative value times a positive value, whichever sign fxx is, and then it's going to switch sign, right? So if this quantity is negative, then it's going to be a saddle point no matter what. So that's the proof. It's not too insightful as far as it just works out that way. And this, after completing the square and multiplying out, that happens to be the key factor that determines what happens to this. But I know some of you wanted to see the proof, so here it is. Okay, that's it for this video. I'll see you later.